Estimating the cost of conduit openings in a surface-mounted electrical metallic tubing or EMT installation involves considering several factors. These factors include the size of the opening, the type of wall or ceiling material you're working with, and prevailing local labor rates. A small opening, typically ranging from 1/2 inch to 1 inch, can generally cost between $20 and $40 per opening. A medium-sized opening from 1.25 inches to 2 inches typically costs between $40 and $60 per opening. Larger openings, those 2.5 inches and above, will generally range from $60 to $100 per opening. For a fire station that's 5,620 square feet, you can estimate the total number of conduit openings needed. A rough estimate would be around 100 to 150 openings. If you are primarily using small openings, the estimated total cost could range from $2,000 to $6,000. If you anticipate mostly medium-sized openings, that total could range from $4,000 to $9,000. And if the project requires mostly large openings, the total estimated cost can be anywhere from $6,000 to $15,000. Remember, this is just an estimate. The actual cost can fluctuate depending on the specific needs of the project. It's always best practice to obtain a detailed and itemized quote from a licensed electrician for an accurate and comprehensive cost estimate before submitting any bids. Firstly, consider the size of the conduit. Smaller conduits, such as 1/2 inch and 3/4 inch, are typically used for branch circuits feeding lighting or receptacle outlets. These require smaller openings and are less labor-intensive. Larger conduits, such as 1 inch, 1.25 inches, 1.5 inches, and 2 inches, are often used for feeder circuits, main pile feeds, or where a larger number of conductors are required. These necessitate larger openings and more installation time. Secondly, evaluate the type of wall or ceiling material. Openings in drywall are generally less expensive than openings in concrete or brick. Concrete and brick require specialized tools and more time to create clean and precise openings. Thirdly, analyze accessibility and working conditions. Openings located in easily accessible areas will be less expensive than those in hard-to-reach places. For example, high ceilings or confined spaces will increase the labor time involved. Fourthly, assess local labor rates. Electrician labor rates can vary significantly depending on location, experience, and union affiliation. Be sure to research the prevailing rates in your area to ensure an accurate estimate. Fifthly, take into account the type of conduit fitting being used. The type of fitting used to connect the conduit to the electrical box or equipment can also affect the cost. Some fittings require more precise openings than others. Sixthly, consider the number of bends in the conduit run. Each bend in the conduit requires additional measurements, cutting, and fitting. This will add to the overall labor time and cost. Seventhly, evaluate the height and complexity of the installation. High ceiling installations, or runs that need to navigate around numerous obstacles, will naturally take longer. Eighthly, analyze the need for fire stopping. In some cases, fire-stopping material may be required around conduit penetrations to maintain the fire rating of the wall or ceiling. This will add to the material and labor costs. Ninthly, make note of the number of conductors within each conduit. The number of conductors being pulled through the conduit can influence the size of the conduit and, therefore, the size of the opening required. Tenthly, consider the overall project size and scope. Larger projects may offer economies of scale, potentially lowering the per opening cost. Factors influencing EMT conduit installation costs include, firstly, material costs. The price of EMT conduit, fittings, and other materials can fluctuate depending on market conditions and supplier pricing. Secondly, labor costs. Electrician labor rates vary based on experience, location, and union affiliation. Thirdly, permit and inspection fees. Local jurisdictions often require permits and inspections for electrical work, adding to the overall project cost. Fourthly, equipment rental. Specialized tools and equipment, such as conduit benders and threading machines, may need to be rented, increasing costs. Fifthly, project complexity. Intricate conduit runs with numerous bends, offsets, or height variations require more labor and expertise. Sixthly, site conditions. Obstacles, limited access, or hazardous environments can impede installation and add to the cost. Seventhly, design specifications. Specific requirements outlined in the project drawings or specifications may necessitate additional materials or labor. Eighthly, code compliance. Adherence to the National Electrical Code, or NEC, and local electrical codes is crucial and can impact material and labor choices. Ninthly, project schedule. Tight deadlines or expedited schedules may necessitate overtime labor, raising the overall cost. Tenthly, rework or changes. Unexpected changes or errors during installation can lead to rework, increasing both material and labor expenses. The National Electrical Code, or NEC, provides guidelines for electrical installations including EMT conduit systems. Here are several key aspects of the NEC that relate to EMT conduit installations. Article 300 of the NEC covers general wiring methods and materials, including requirements for mechanical strength and securing and supporting wiring. Article 344 specifically addresses EMT conduit, outlining acceptable uses, installation requirements, and size and guidelines. Section 300.4 deals with protection against physical damage, requiring that EMT conduit be protected from damage where subject to physical impact. Section 300.5 covers underground installations, specifying burial depths and protection requirements for EMT conduit installed underground. Section 314.16 outlines the requirements for box fill calculations, ensuring that electrical boxes are not overcrowded with conductors and devices. Section 314.17 addresses the proper use of conduit bodies, such as LB fittings, to provide access to conductors for pulling and maintenance. Section 358.10 specifies the number of conductors allowed in EMT conduit based on conduit size and conductor fill percentages. Section 358.12 outlines permitted and not permitted uses of EMT conduit, such as in corrosive environments or where subject to severe physical damage, unless properly protected. Section 358.30 details the requirements for securing and supporting EMT conduit at specific intervals to ensure its mechanical integrity. Section 358.42 addresses the proper use of couplings and connectors for joining EMT conduit sections and connecting conduit to boxes and equipment. When bidding an electrical job involving EMT conduit, it's crucial to understand and account for all relevant NEC requirements to ensure a safe and code-compliant installation. Estimating conduit fill involves calculating the total cross-sectional area of all conductors within the conduit and comparing it to the allowable fill percentage specified in the NEC. This ensures that the conduit is not overcrowded, which can lead to overheating and insulation damage. The NEC provides tables in Chapter 9 that list the dimensions and cross-sectional areas of various conductors and conduit sizes. To calculate conduit fill, firstly determine the type and size of each conductor. Secondly, find the cross-sectional area of each conductor from the NEC tables. Thirdly, multiply the cross-sectional area of each conductor by the number of conductors of that size. Fourthly, add up the total cross-sectional area of all conductors in the conduit. Fifthly, determine the conduit size being used. Sixthly, find the allowable fill percentage for that conduit size from the NEC tables. Seventhly, multiply the cross-sectional area of the conduit by the allowable fill percentage. Eighthly, compare the total cross-sectional area of the conductors to the allowable fill area of the conduit. The total conductor area must not exceed the allowable fill area. If the conductor area exceeds the allowable fill area, a larger conduit size must be used. Example, consider a conduit containing 3 number 12 AWGTHHN conductors and 2 number 14 AWGTHHN conductors. From NEC Table 8 in Chapter 9, the cross-sectional area of a number 12 AWGTHHN conductor is 0.133 square inches and the cross-sectional area of a number 14 AWGTHHN conductor is 0.97 square inches. The total cross-sectional area of the number 12 AWG conductors is 3 multiplied by 0.133, equaling 0.399 square inches. The total cross-sectional area of the number 14 AWG conductors is 2 multiplied by 0.97, equaling 0.194 square inches. The total cross-sectional area of all conductors is 0.399 plus 0.194, equaling 0.593 square inches. If a 1/2 inch EMT conduit is being used, Table 4 in Chapter 9 allows a 40% fill percentage. The internal area of a 1/2 inch EMT conduit is 0.304 square inches. The allowable fill area is 40% of 0.304, equaling 0.1216 square inches. Since the total conductor area of 0.593 square inches is less than the allowable fill area of 0.1216 square inches, a 1/2 inch EMT conduit is sufficient for this application. For estimating labor hours for EMT conduit installation, several factors need to be considered. These include the complexity of the run, the height of the installation, the type of mounting surface, and the presence of obstructions. Straight runs of EMT conduit in easily accessible locations will require less labor than complex runs with multiple bends and offsets in difficult-to-reach areas. Consider the following guidelines for estimating labor hours. For straight runs of EMT conduit on open walls or ceilings, estimate 1 to 2 hours per 10 feet of conduit. For runs with 1 or 2 bends, estimate 2 to 3 hours per 10 feet of conduit. For runs with multiple bends or offsets, estimate 3 to 4 hours per 10 feet of conduit. For high installations, add 25 to 50% to the labor hours. For installations on concrete or masonry surfaces, add 25 to 50% to the labor hours. For installations with numerous obstructions, add 25 to 50% to the labor hours. These are just estimates, and actual labor hours may vary depending on the specific project conditions. It's always best to consult with experienced electricians to get an accurate estimate. Consider an example where you have a 50-foot run of EMT conduit with 3 bends installed on a concrete wall at a height of 12 feet. Base labor for 50 feet of conduit with bends would be 5 multiplied by 3 hours per 10 feet, totaling 15 hours. At 25% for concrete wall insulation, 15 multiplied by 0.25 equals 3.75 hours. At 25% for high installation, 15 multiplied by 0.25 equals 3.75 hours. The total estimated labor hours would be 15 plus 3.75 plus 3.75, equaling 22.5 hours. Estimating electrical material costs involves obtaining current pricing from suppliers for all the necessary materials. This includes EMT conduit, fittings, boxes, wire, and other components. Prices can vary depending on the supplier, quantity purchased, and current market conditions. Firstly, create a detailed bill of materials, listing all the items needed for the project, with specific quantities and sizes. Secondly, obtain pricing from multiple suppliers, comparing prices and lead times. Thirdly, factor in any discounts or bulk pricing that may be available. Fourthly, add a contingency for unexpected material costs or price increases. Fifthly, include sales tax and shipping costs in the total material cost estimate. A sample bill of materials for small EMT conduit project might include the following items: 100 feet of 1/2 inch EMT conduit, 20 1/2 inch EMT couplings, 10 1/2 inch EMT connectors, 5 4-inch square electrical boxes, 5 4-inch square box covers, 20 wire connectors, 100 feet of number 12 AWGTHHN wire. After obtaining pricing from suppliers, the estimated material cost can be calculated. For example, if 1/2 inch EMT conduit costs $2 per foot, the cost for 100 feet would be $200. If 1/2 inch EMT couplings cost $0.50 each, the cost for 20 couplings would be $10. If 1/2 inch EMT connectors cost $0.75 each, the cost for 10 connectors would be $7.50. If 4-inch square electrical boxes cost $3 each, the cost for 5 boxes would be $15. If 4-inch square box covers cost $1 each, the cost for 5 covers would be $5. If wire connectors cost $0.10 each, the cost for 20 connectors would be $2. If number 12 AWGTHHN wire costs $0.20 per foot, the cost for 100 feet would be $20. The total estimated material cost for this project would be $200 plus $10 plus $7.50 plus $15 plus $5 plus $2 plus $20, equaling $259.50. For fire stopping requirements around conduit penetrations, the NEC and local building codes dictate the types of materials and methods that must be used to maintain the fire rating of walls and ceilings. When EMT conduit passes through a fire-rated wall or ceiling, the opening around the conduit must be sealed with an approved fire-stopping material to prevent the spread of fire and smoke. Firstly, identify the fire rating of the wall or ceiling. Secondly, select the fire-stopping material that is rated for the same or greater fire rating. Thirdly, install the fire-stopping material according to the manufacturer's instructions. Fourthly, inspect the installation to ensure that it is properly sealed and meets code requirements. Common types of fire-stopping materials include fire-rated caulk, fire-rated foam, and fire-rated sleeves. The cost of fire-stopping materials and labor can vary depending on the size and number of penetrations. An example where a 2-inch EMT conduit passes through a 2-hour fire-rated wall, the opening around the conduit must be sealed with a fire-stopping material that is rated for at least 2 hours. Fire-rated caulk could be used to seal the opening, ensuring that it is completely filled and flush with the surface of the wall. Proper documentation of the fire-stopping installation is essential for code compliance and future inspections. Estimating voltage drop in EMT conduit installations is crucial to ensure that electrical equipment receives the proper voltage for optimal performance. Excessive voltage drop can cause equipment to malfunction, overheat, or fail prematurely. The NEC provides guidelines for calculating voltage drop and recommends limiting voltage drop to no more than 5% from the source to the farthest point of utilization. Firstly, determine the length of the circuit. Secondly, determine the conductor size and type. Thirdly, determine the load current. Fourthly, determine the voltage drop per amp per foot from NEC Chapter 9, Table 8. Fifthly, calculate the total voltage drop using the following formula: voltage drop equals 2 multiplied by length multiplied by current multiplied by voltage drop per amp per foot divided by 1000. Sixthly, compare the calculated voltage drop to the allowable voltage drop. Seventhly, if the calculated voltage drop exceeds the allowable voltage drop, increase the conductor size or reduce the circuit length. Consider an example where you have a 100-foot circuit using number 12 AWG copper conductors, supplying a 15-amp load at 120 volts. From NEC Chapter 9, Table 8, the voltage drop per amp per foot for number 12 AWG copper conductors is 3.21 millivolts. The total voltage drop is 2 multiplied by 100 multiplied by 15 multiplied by 3.21 divided by 1000, equaling 9.63 volts. The allowable voltage drop is 5% of 120 volts, equaling 6 volts. Since the calculated voltage drop of 9.63 volts exceeds the allowable voltage drop of 6 volts, a larger conductor size must be used. If the conductor size is increased to number 10 AWG copper conductors, the voltage drop per amp per foot is reduced to 2.1 millivolts. The total voltage drop is now 2 multiplied by 100 multiplied by 15 multiplied by 2.1 divided by 1000, equaling 6.3 volts. While 6.3 volts exceeds the 6 volts recommendation, it is likely acceptable. It's important to consider ambient temperature and conductor bundling when calculating voltage drop, as these factors can affect the conductor's resistance and increase voltage drop. Using online voltage drop calculators can simplify the calculation process and provide accurate results. Always consult the NEC and local electrical codes for specific requirements and recommendations regarding voltage drop.